Hello, everyone, and welcome to our webinar, Method Validation and Improvement in Robustness of Chiral Analytical LC Methods. My name is Tracy Hartledge. I'm a sales representative and project coordinator for Chiral Technologies and will be your moderator for today's session. Presenting today's webinar is Bill Champion, Senior Scientist here at Chiral Technologies. Please note that during the webinar, you will have the ability to submit your questions as they arise. Please look at the control panel on the right side of your screen and click on the Questions tab to begin. Fielding your questions today will be members of our technical team. We have also placed a copy of today's presentation in the handout section of the control panel. I now turn the microphone over to Bill Champion. Bill, the floor is yours.
Thank you, Tracy. Well, good morning, everyone, or good afternoon, depending on where we are. I'm going to talk about method validation, improvement, and robustness of chiral LC methods. As I put this talk together, I realized I had a lot of information. It was going to be a several-hour talk, so I've had to remove some things or skip over a few things or reference them away. But if you have any questions, this is my contact information. Certainly feel free to contact me later, and I would be glad to discuss anything in more detail. This is the organization of my talk. I want to talk about what our objectives are for the talk, what I hope you get out of it. A little bit about equations, just so you're not too concerned. It'll be fairly simple stuff and things you probably have already seen in chiral chromatography. There's some special considerations in chiral chromatography, and I want to talk about the validation of the analytical methods, which I think is what most of you are here for, and something that I think is also at least as of much importance is improvement in the robustness of the analytical methods. Then talk about how we can help, and then I'll show you the summary and conclusion slide. So this is what I hope you learn from this talk. What we know about achiral chromatography applies to chiral chromatography. So it's not a magic process. It's governed by the laws of nature and the same principles we see in other forms of chromatography. It's a partitioning between the stationary phase of the analyte between stationary phase and a mobile phase. The complication comes in that we're just dealing with a more complicated stationary phase, and so it becomes a little more interesting, but also a little more complicated. Hopefully some of the things I tell you will remove a little bit of that complication. And so the parameters, equations that we use in achiral chromatography also apply. Chiral chromatography are also often dealing with quantitative analysis of enantiomers at the 1,000:1 ratio, that is 0.1%. Talk about validation of analytical methods. The key is probably limit of detection, limit of quantitation, because we're dealing with a major component and its minor impurity, and we may have a limit of detection issues. We'll talk about selectivity. You certainly need to have separation between the enantiomers, and accuracy, because this is an important analysis. As I was putting this talk together, I realized or was thinking about the things that I do on troubleshooting, and many of the same tests and questions we have in method robustness are issues around troubleshooting. I don't have time to talk about troubleshooting per se, but I did want to point this out. Many of the things we investigate in method robustness are the same kinds of experiments or tests that we would do in troubleshooting. I like to use a systematic approach to method development or to troubleshooting, and so I think I'm going to show you some examples of that. I think what happens is it's a little bit front-end loaded. You do a few more experiments on the front end, but the advantage is you get much better understanding in the long run. Do probably fewer experiments, and it gets you to an optimum or to a good position fairly quickly. It also lets you know how you got there, so you know what parameters are important and maybe what are not. I sometimes deal with people who have a problem with their method, and they have maybe a complicated mobile phase, and I'll ask them about the different components, and they don't always know why they have those components in there, but the answer has come back a number of times. Well, that's the conditions we were using when we found a separation at work. So oftentimes we don't need to use complicated mobile phases or complicated separation conditions. We want to keep the method simple. The simpler it is, the fewer components there are have a problem or to go wrong. So there's the robustness of the method is better generally if you have a simple method. Okay, I have a few equations to show. The things I like about using equations is that they are a succinct expression of the relationship between the parameters and some effect like resolution or retention or something like that. These are fairly simple equations, no quantum mechanics, no matrices, no imaginary axes. And these are all equations that you probably, and parameters that you're familiar with from achiral chromatography. What I would do is I would refer you to fundamental textbooks in chromatography. Even gas chromatography discusses these things in ways that generally are applicable to liquid chromatography. Some of the specifics are different, but we're still dealing with the partitioning between a stationary phase and a mobile phase, and these are equations to describe that behavior. Chromatography is a separation technique, so probably our fundamental equation is the resolution equation, just a measure of how good the separation is. So we can improve resolution by increasing the difference in retention time between the analytes or decreasing the peak width. We can expand this equation. It's just the difference in the retention times of the two analytes, and then some measure of the peak width, such as the arithmetic mean of the two components. We have a divisor in the denominator, so that just comes up as the into the numerator, and this makes a arithmetically more straightforward calculation. There's less ambiguity or confusion about what to do with a 1 over a reciprocal in the denominator. But if we make some substitutions, do some algebra, we get an equation that looks like this. There's several forms of the resolution equation. I would refer you to this. Joe Foley has done, I think, a really nice job of discussing that in this publication. Fundamentally, the equations look like this, but based on some of the assumptions or the ways that you want to make measurements, you may get slightly different terms. I'm not going to go into that, but that could be important. But for our purposes, an equation like this is perfectly acceptable. A couple of things this equation tells us is these are multiplied together. They're independent terms, so we can affect column efficiency, retention, or selectivity independently and improve resolution. So N, or column efficiency, is just related to the particle's diameter. So 1 over the particle size is related to the column efficiency. If you increase column length, you increase column efficiency or number of theoretical plates. Retention factor is a fundamental measure of the retention. Weaker mobile phase gives us more retention. By definition, that makes a weaker mobile phase. For example, in reverse phase chromatography, if we have less acetonitrile and more water in our mobile phase, we expect longer retention. Selectivity is a little more difficult because it's more complicated. It's interaction of the analyte with the mobile phase and the stationary phase, and it is affected by temperature. So this is more experimentally driven, so that makes it maybe a little more interesting, but it's less predictable. The greatest effect in resolution in liquid chromatography comes from changes in selectivity, which symbols are usually use A or alpha. Selectivity is most effectively changed by modifications of the mobile phase and or stationary phase, and the temperature has an effect. But as I said, these are independent terms, so we can make changes to each one of these individual terms and affect the resolution without significantly affecting the other terms. And this is a little bit of a problem in chromatography. There is a diminishing return on each of these terms in improving resolution. And this is just some graphs. Since resolution increases as a square root of the number of theoretical plates, if you want to double your column efficiency, if you want to double the resolution, you have to have a 4-fold increase in column efficiency. Or if you double column efficiency, you only get a 1.4 square root of 2 improvement in resolution. Retention factor, and we'll describe the equation of that in a moment. If you increase the retention, the improvement in resolution starts to drop off after maybe 5 or so initial column volumes or retention factor of 5 or so. So if you go from 5 to 10, you double the retention time, but you make a relatively small improvement in the retention, in the separation. Selectivity also is diminishing return. Selectivity, we have to be a little careful that we don't have too much selectivity, because if you have a huge difference in the retention, it just uses up time, and as we'll show, the later eluting peak is usually much broader than the first eluting peak. So there is an optimum for selectivity. These are just some of the calculations of these terms. Retention factor is just the ratio of it's a partition coefficient, the amount of time the analyte spends in the stationary phase with respect to the time it spends in the mobile phase. The total time is the time in the stationary phase and the time in the mobile phase. The time in the mobile phase is really, the analyte moves at about the same velocity or the same velocity as the bulk mobile phase when it's in the mobile phase. So we can substitute T0 is the same time as the mobile phase, and we can't know the time in the stationary phase, but we know it's a difference in the time in the stationary phase and the mobile phase. So this is a fairly simple calculation. It looks a little arcane, but if you think of it really as a partition coefficient, that becomes fairly useful. You see it's dimensionless, that means it's unaffected by column length or flow rate, and so we can transfer this from one column length to another, or one flow rate to another. We'll know about retention factor. Theoretical plates, calculations for these, or the derivation of this is a little complicated. It involves some statistics, but the fundamental issue is the theoretical plates are related to the square of the ratio of the retention time and the peak width. So you can see that the retention time, square root of the retention time determines the width of the peaks. Selectivity is defined as a ratio of the retention factors, but we just can't, everything spends the same amount of time in the mobile phase. It's just the retentions determine how much time it spends in the stationary phase. So this is just a ratio of the time the two analytes spend in the stationary phase. So spend an identical amount of time in the stationary phase, they'll co-elute to be an alpha of 1. If they spend a dramatically different or a different time in the stationary phase, it'll be some number related to that ratio. So if one of them spends twice as much time in the stationary phase as the other one, you'll have a selectivity of 2. And as I indicated, this is a resolution equation. And as we'll see, this is just column efficiency. So this is related to the stationary phase. The selectivity is related to the mobile phase and the chiral stationary phase, and also the retention. These are still independent parameters. It's just that these two changes can affect these parameters differently. And all of these are related to temperature. That's a lot of information very quickly. These are equations that you probably are familiar with from dealing with reverse phase chromatography. If you're not real familiar with them, I think that probably would help you in your achiral chromatography. Just do a little reading in fundamental text on liquid chromatography. Discussion is much more in depth than what I just went through. So there are some special considerations in chiral chromatography. The principles of chromatography apply to chiral chromatography. As I said earlier, chromatography is a partitioning of the analyte between stationary phase and mobile phase. So these equations that I showed you a little bit ago apply whether it's chiral chromatography or achiral. What makes chiral chromatography somewhat mysterious or difficult is the separation mechanism is a little more complex than, say, reverse phase chromatography. We typically have weak polar stereoselective interactions between analyte and chiral stationary phase. The effect of the mobile phase is often more pronounced in chiral chromatography than, for example, in achiral chromatography. So this will give us an extra parameter to change, but it's also an extra parameter to investigate. We're dealing with often the analysis of the wrong enantiomer. We're usually interested in what the level of the impurity enantiomer, the undesired enantiomer is. Usually don't analyze racemates. In chiral HPLC, the separation is typically driven by selectivity, and the isomer ratio is usually a factor of 100 to 1 or 1,000 to 1 or 2,000 to 1. So I just talk a little bit about the chromatography. I want to talk about the particle size or column efficiency. And you probably know this from achiral chromatography, that with smaller particles, we get higher efficiencies related to 1 over the diameter of the particle. So as we go to smaller particles, we'll get higher column efficiency, which means we'll get higher resolution. But we also get higher pressure, and this certainly is the issue of UHPLC. UHPLC, as you probably know, is not really a technique. It just means chromatography run using smaller particles, which result in higher pressure. But with smaller particles and sharper peaks, we also get taller peaks. The area is conserved, so we'll get a taller peak, which improves our limit of detection, limit of quantitation. So this can be very valuable in performing an analysis of the low-level enantiomer. There's also some advantages to using a shorter column. We have shorter analysis time. Obviously, from the shorter column, we have lower pressure, so we may be able to run at higher flow rate even and reduce analysis time further. As we discussed earlier, the retention factors are unaffected by flow rate. And this is a little counterintuitive, but on shorter columns, you also get taller peaks. This is a summary of what I just said. This is a little clue as if you want to work this out for yourself, but because the peak width changes as a square root of the column efficiency, if we say double the column efficiency by making the column longer, the peak width only increases as a square root of 2. So we will have a higher or a sharper peak relative to the retention time on shorter columns. And that's often discussed in fundamental books on chromatography. If you want to discuss it, I'd be glad to talk to you about it. And I will say I've had discussions with people who are very good chromatographers who have had to think this thing through, that it seems intuitively that, oh, longer columns should give you a higher column efficiency, and therefore the peaks will be sharper. So as we go from smaller particles, we do increase the column efficiency. So we have about a 5/3 increase in the column efficiency, going from 5 micron particles to 3 micron. And we have the equivalent decrease in column efficiency going to the shorter column of about 3/5. Those cancel out. So for going from 5 micron to 3 micron and going from 250 millimeters to 150 millimeters, we should have about the same column efficiency, but we have about 60% of the analysis time. So we've reduced the analysis time. These peaks are not on the same, they're on the same time scale, but not the same response scale. But we can see that these peaks are sharper, so they will be taller because area is conserved. So this gives us an advantage. We see the same general behavior going from the smaller particles. I want to point this out. This illustrates two things. One is, this isn't just a change from particle size. This, I think, is probably just a lot-to-lot variability. So, and we'll discuss this, and we do this in achiral chromatography too. We'll use multiple lots in part of our validation, different lots of stationary phase. But one of the other issues is you don't want to have just good enough separation in your method when you develop it. You want to have some leeway so that if there is some variability in instrument to instrument, or some variability in a stationary phase or whatever, that you have enough resolution to overcome some slight differences in the observed resolution with your method. So part of making a robust method is not to have just barely have separation. You want to have plenty of resolution. We go to a smaller particles yet, go from the 3 micron to sub 2. We get further increase in sharpness of the peak. Again, not on the same time response scale, but these peaks are taller because the area is conserved. And we got back some of our resolution, partly because we went to smaller particles, but also probably a lot-to-lot difference. And I'd certainly point out again, the lot-to-lot variability is an issue you probably have encountered in achiral chromatography. Separation mechanism in chiral separations is different than we typically see in reversed phase or normal phase or helix or other separation techniques that you may be familiar with. In achiral chromatography, we're used to seeing things like C18, which is fairly lipophilic stationary phase and pretty first order interaction between analyte and stationary phase, just a partitioning principally on bulk polarity. We can add some functional groups and change maybe a little bit of selectivity and add some polarity, so increase the retention of polar compounds. But basically, we're looking for a single mode interaction. They're fairly predictable. Don't want to spend a lot of time on this slide, but it shows us a lot of things. We know something about allotropic strength of alcohol, like methanol versus acetonitrile. We know ACN is a stronger solvent, so typically 40-60 acetonitrile water is the same allotropic strength as methanol 50-50. I think in the tables that I was looking at, it was like 41-50. So that's the mobile phase I used, and we get almost identical separation. There's a little less retention in acetonitrile for these benzyl alcohols. But notice this order of elution is predictable. The more polar the compound, the less it's retained. So the toluene, which is just a methylbenzene, is the most retained. It's the most lipophilic. This ether, anisole, is more polar than toluene, so it's less retained, and the benzyl alcohol is even more polar, so it's more retained. Notice both of these compounds have stereogenic or chiral center, so either the parafluorophenethanol or phenethanol itself are the enantiomers are resolved. We have an achiral column, so we're not going to get any difference in behavior for the enantiomers on that column. To get separation of chiral compounds, we need to use a chiral stationary phase. So the interactions of the analyte with the stationary phase, instead of being bulk properties, are generally stereoselective or stereospecific interactions. They're generally weak polar interactions, so hydrogen bonding, dipole-dipole interactions, pi-pi bonding, etc. So in this example, if we have stationary phase, which has, just to make up examples, say a hydrogen bond acceptor, and this is a pi base, and this is a dipole. If we have a hydrogen bond donor and we have a pi acid and we have the dipole of the opposite orientation, these will interact strongly, and so there's a good chance we'll have good retention. If we have the fit isn't so good, if we may get retention between, say, the hydrogen bonding, but the pi base and the dipole may not fit as well as the pi acid pi base, and same thing here with the pi acid and the other dipole, and so we may get less retention, less good fit, and so we get it's less retained. Good fit can sometimes come at a price. We have more interactions. Think about in achiral reverse phase chromatography, we deal with the dreaded secondary interactions, such as the interaction of amines with silanols. We try to disrupt that secondary interaction. Here, we don't have secondary interactions, we have tertiary interactions at a minimum. Sometimes we have quaternary or higher levels of interaction. We have 4, 5, 6 chiral sites that may interact with the isomers. We need at least 3, but we sometimes have more. So there's always a possibility of having, say, a sluggish off rate with one of these interactions. And so often the more retained compound is broader and may sometimes tail in chiral separations, more so than you would predict in say, typical reverse phase chromatography. Separations are less predictable in chiral chromatography. That can make them interesting, but that can also make it challenging. This just shows, I won't get into stationary phases, but we have difference of retention. Chiral-Pac IA is one of our best columns. We find a lot of separations on IA. In this case, it didn't give very good separation. Chiral-Pac IB gave a little bit better, and Chiral-Pac IC gave even better. Well, look at the structure of the molecule, know the structure of the stationary phase. Very difficult to predict that. We have to do that as an experimental process. So we typically just do column screening and typically use a fairly strong mobile phase just so we make sure everything comes off fairly quickly. In this case, on our Chiral Pack IF, we got pretty good separation. We got some retention of IE and a little bit of retention on ID. So we probably investigated those using weaker mobile phase. In fact, on the ID, using a weak, going from 50-50 hexane ethanol to 80-20, we in fact did find a separation. This actually came from one of our application notes. I didn't do this experiment, but in looking at it, I would have thought, okay, we got the retention factor is around 5 or so. So I would have thought we could probably reduce retention and still get a pretty good separation. And so thinking about kind of the backwards way of thinking about this diminishing return is, on the other hand, if there's a diminishing return and an increasing retention factor for improving resolution, maybe if we decrease retention, we pay a small price and less resolution. So I don't have the experimental details, but I would expect that we would probably get faster analysis with going to lower retention and probably still have adequate resolution. But it'd be certainly an experiment worth running. So maybe try 70-30 on this. This just shows retention factor of, on this column, about 2.7 milliliters for a 250 millimeter column. So 1 mil a minute, that'd be about 2.7 minutes. So there's 1, 2, 3, 4, 5 additional column volumes. So it's a retention factor of 5. We also see differences in retention on different stationary phases. OD and AD are somewhat similar stationary phases, but we got reversal of elution order. This is the UV chromatograms, and this is just, we have an inline polarimeter with this analysis. And this just shows that, sure enough, you can have a reversal elution order. So sometimes people will talk to me about the first isomer, or first enantiomer. It depends on, that's not a physical property. It depends on the which stationary phase you're using, or mobile phase, as we'll see. This can present a problem with racemate. You don't necessarily know what the order of elution is. So either you need to have the individual isomers, or you need to have an inline polarimeter, but then you still need to know optical rotation of the isomers. The other thing I want to point out, this is some work we did with the US EPA on some organophosphorus pesticides. Phosphate is is tetrahedral. See the little tetrahedron, and so just like carbon, so it's also can have a stereogenic or chiral center. So many of the organophosphorus pesticides are in fact chiral. The mobile phase is often more pronounced in chiral chromatography than example in Achiral LC. And I showed you the example of Achiral in reverse phase chromatography, where changing acetonitrile or methanol to acetonitrile caused very little difference in the actual selectivity. In chiral separations, it can be dramatic because different alcohol can have slightly different interactions with facilitating the interaction of the analyte with the stationary phase, or the orientation of the stationary phase, or the orientation of the analyte with respect to each other. So in screening, I would have run methanol, ethanol at a 1-to-1 ratio. When I saw this, I thought, well, this is interesting. Let's see, probably in changing one of the alcohols will, increasing one of the alcohols would improve separation. I had an inline polarimeter, but I also had isolated or separated these enantiomers, so I had spiked the sample with one of the enantiomers so that I could track order of elution in screening. So as I went to 3-to-1 methanol to ethanol and 1-to-3 methanol and ethanol, I saw a difference in retention. I got or separation. I got an improvement in separation, putting more methanol in the mobile phase. Looked like they co-eluted with more ethanol or less methanol in the mobile phase. So I thought, well, we probably just ought to try 100% methanol. That's probably going to give a pretty good separation. I wasn't thrilled with the tailing peaks, but it was probably adequate for this analysis. But I also thought, well, let's just see what happens with ethanol. Are we going to get any additional separation, or do you suppose we might just have an order of elution reversal? And sure enough, the elution order reversed. So ethanol to methanol, we would not expect, we wouldn't use ethanol in reverse phase chromatography typically because of the viscosity, but we would expect a pretty similar chromatography. And sometimes in chiral separations, we see this no difference. Sometimes we see a big difference. This is not particularly important to this separation, but it illustrates an example. So if we have a single component ratio of the alcohols, we can plot their effect on the retention of the two enantiomers. And just looking at this plot, we can see that the minus isomer, as we increase the ethanol concentration, the retention time decreases. And I guess we could have seen that just by inspection, looking at that. But by plotting the data, that gives us an idea of how it works. I just use Excel just to connect the dots, so to speak. The plus isomer, interestingly, the minimum retention occurred at like a 1-to-1 ratio of methanol to ethanol, and we got more retention with 100% methanol and 100% ethanol. That's not particularly important in this separation, but this is the sort of thing that you may want to know in doing method development or method troubleshooting or method validation. And so I think plotting the data, if I just looked at 1 or 2 data points, particularly if I looked at this one and looked at this one, especially if I'd not had a way of isolating the two enantiomers, such as a chiral detector or a difference in a concentration, I would have thought, oh, it doesn't matter whether we go from methanol or ethanol. But by increasing a few data points, I think we can see in a systematic way how the behavior occurs. Again, this is probably not particularly profound for this example, but it'd be a little more noticeable in some additional following examples. So we're analyzing the wrong enantiomer or the undesired enantiomer. So the isomer ratio is typically like 100 to 1 or 1,000 to 1, 2,000 to 1. So analysis of racemate is, by comparison, easy to analyzing for the minor enantiomer. And in this example, this was on a separation, I think, on a chiral pack IA. As we decrease the amount of IPA or isopropyl alcohol, we make the mobile phase weaker, and we get kind of an expected increase in retention. And we also have an increase in separation. So we have several conditions that we can choose. This is fairly straightforward. Notice that we get a little more tailing. Notice the peaks are a little shorter. Part of this, I think, is a little bit of column overload. I had shot a very concentrated sample just because I didn't know how much response I was going to get. So the analysis of the low-level enantiomer is a bit of a challenge. And for these two enantiomers, excuse me, for this pair, we got nearly baseline separation. If you just look at the chromatogram, you say, well, this is penetration to baseline. We do that all the time. Peak height was about 1,500 milliabsorbance or 1,500 milliabsorbance units. So this is only a fraction of the peak height. So this is an insignificant amount of area of this peak that bleeds into this peak, but correspondingly, you get a similar amount of area from this peak bleeding into this one. So penetration to baseline is a reasonable way to do the integration for these two peaks, and it's very reliable. The peaks get smaller, and there's not quite as much tailing. Peak width's a little sharper just because of the column overload problem. So it's not a problem, but at low-level components. But think about what happens as we bleed some of this isomer into this more retained peak. So notice that we get a little bit of, so you just kind of extrapolate the exponential decay in from this peak into here, and you think, well, in this region here, we get a little bit of this contribution of this peak to the area of this peak. At say 2%, it's probably not significant. It may be measurable, but it's not very, very large. But what about at 0.1% or 0.2% or 0.1% or 0.05? You can see that could be an appreciable area, and we would have biased the retention, bias the area high. But if we look at how much the front peak or the tailing peak bleeds into the front peak, we see, well, that's not so much. And in fact, you can see that these peaks probably have no bleed of the later eluting peak fronting into the second peak. So in general, we would want to have our low-level enantiomer elute first if we can. Two advantages: one, the first peak is usually taller, and the other is there's less interference from the later eluting peak. Can't always do that, but at least you need to be aware that you can have some tailing of the first peak into the second peak. And good LOD, LOQ requires quiet baseline. We'll talk about this a little bit more in a later slide. So now we'll talk a little bit. These are some of the issues around chiral chromatography. So now we want to talk a little bit about validation of analytical methods. So much of what we've done in achiral chromatography, we're going to do here. We'll worry about things like precision, things that are related to the accuracy, limit of detection, the robustness of the method, the stability of the sample. So I'm not going to go into the precision because that's fairly straightforward. I think most people are well aware of these things, but we do want to know how good our when we run an analysis and we make multiple injections or multiple preps, is this reliable? What about if is this going to be a technique dependent? Is it really going to matter how the analyst actually performs the experiment? There's some really technique dependent steps. What about the equipment? Does it matter whether you use a UHPLC or a more instrument that maybe came from a previous century and has a little extra column band broadening? Does it matter, or maybe a longer delay time? Is there a lot-to-lot variability, and so on? And then certainly the collaborative study between laboratories. So these are things that we worry about in achiral chromatography. We also can worry about them in chiral chromatography. Accuracy, these are related to the accuracy, this is getting reproducible results. This is getting the right result. And so these, there may be a few issues just because we're really dealing with a low-level component, but it's no different than we would treat impurities in achiral chromatography. So we want to demonstrate good resolution between the isomers. And as I talked about before, that, for two major components, that's probably pretty good. It's probably pretty good if we have two level components. We might have a problem if we have one high and one low. But enantiomers have the same UV spectrum. They're just mirror images, so the UV spectrum in a chiral solvent will be identical. They have the same mass, so you have the same mass spectrum if you analyze them by mass spectroscopy. They will have opposite rotation. If they're the same level, you'd expect similar rotations. And if you have a racemate, you would expect them to have the same UV area. And so you want to maybe confirm all of those things. I think that's pretty straightforward. It's almost too easy. I don't want to get into this, but there's something about enantiomeric excess, and sometimes people report the results in chiral separations in enantiomeric excess, and it's archaic, but it's not wrong. It's an acceptable way to do it. I think it's unnecessary, and I think it actually is. It's just confusing, but the transformation between enantiomeric excess and chiral purity is doable. We use the same numbers. It's just we look at the difference between the desired enantiomer or right enantiomer and the wrong enantiomer divided by the sum of the two enantiomers times 100%. And this comes from pre-chiral chromatography days, when the only way to measure the enantiomeric excess or the enantiomeric purity was to do an optical rotation based upon what you would expect the optical rotation to be. The wrong enantiomer gives opposite response for the desired enantiomer, and it kind of cancels out. So how much rotation you get is just the difference between the two enantiomers. For racemate, there's no optical rotation. But it is archaic, and it is a little confusing. I think a more reasonable way to do it is just measure it as a chiral purity like you would any other impurity, just the area or the response of the wrong enantiomer divided by the concentration of the area of the correct enantiomer. Probably should use correct instead of right because the right-handed, left-handed issue, but of the correct enantiomer times 100%. And I think just treat it like a regular impurity is the way to do it. But people do it both ways, and we can get into a discussion about that. It's not worth it. I think either way is the numbers are you can transform them. It's like the difference between Fahrenheit and centigrade. So linear range, we are dealing with the ratio, so we are really dealing with the area percent, but the dynamic range of UV detectors on the order of 1,000 to 1,500 milliabsorbance units. That makes 0.1% on the order of 1 milliabsorbent units. So the dynamic range will depend on the signal noise of the minor component. And LOD and LOQ obviously depend on the signal to noise. So the couple of issues around signal to noise, and it does require a quiet baseline, for example, or you can increase the signal noise by having a quiet baseline. And one of the things that we want to do is, and this is an achiral compound, I just chose this spectrum because it has some things I want to point out. But you want to change the UV, you want to obtain the UV spectrum if possible. So you want to select a wavelength with good response. Well, in this region around 200, usually the diode array detectors, for example, can sort of go down, well, they can go down to 190, 200 region, but most of the solvents we have absorbance in this region. So their UV cutoffs are somewhere around, depending on what solvent it is, methanol I think is around 205. So you may get some response background due to the solvent. Just attenuate your response, it shouldn't interfere. They won't, but we usually want to use a wavelength a little longer than say 200 nanometers or 210 or something like that. We want to use a wavelength around, it's a little longer than that. It's above the UV cutoff of the mobile phase, and it's also not in a region where everything absorbs. So you're not going to have as many bumps in the baseline. If you have things in the mobile phase, such as diethylamine, trifluoroacetic acid, they can cause some disturbance of the baseline, some background response. And I think if you observe, probably has observed that with TFA in the mobile phase below a wavelength of, below 220 or something like that, the baseline is a little noisier than it is at longer wavelengths. People sometimes choose 254 nanometers as their wavelength, and this comes from, in the old days, we had just single wavelength detectors, and they used a mercury lamp at a really sharp emission band at 254 point something nanometers. It was very quiet. It was an excellent detector if your analyte had good absorbance at 254. With the deuterium lamp, we don't get, 254 is not a special wavelength for the deuterium lamps. There's no real reason to choose 254. It's just a historical wavelength, and people often choose it. In fact, for this compound, it would be a poor choice if we're trying to improve sensitivity because it has very poor absorbance. We probably want a wavelength around here. Notice in aromatic compounds, we often see somewhere in here we have some absorbance by aromatic compounds. So if you have a lot of impurities that are aliphatic, and you just want to focus on the aromatic compounds, you might want to use this. But I think get a UV spectrum, so you deliberately choose a wavelength. If you don't have a UV spectrometer, you can use a very short column. It doesn't even have to be a chiral column. You can use a reverse phase column, for example, and obtain a wavelength or a guard column even, and just inject your analyte, repeated injections at different wavelengths, and you can kind of manually construct at least an approximation of UV spectrum. So robustness investigates small changes around method conditions. Talk about robustness, I'm going to talk about big changes for making the method robust, but as far as validation, we want to see, well, what kind of the small changes if we have one instrument to the other has a small difference in the flow, or the mixing of the mobile phase, or the injector, or the calibration of the wavelengths, do they make a quantitative change in the results? And this is a table that I think we could assemble, and this is unrelated to chiral chromatography. This is something that you would do with an achiral separation too. So this is just sensitivity to small changes. So if we make small changes in the flow rate, do we see differences that might affect the analysis? Make small changes in the mobile phase, what we'd expect, change in retention generally, and certainly in reverse phase chromatography we would. Do we get change in selectivity? Oh, maybe not, just resolution change, and so on. We just go through this, but the idea is you make small changes, a few percent of the specified conditions, and see, does that affect your separation in a way such that it causes a problem? If you have a yes, and that it affects the separation in a way that causes a problem, then you want to be sure that you set a very tight specification on that, or you have a way to account for it. That is, well, if it has this kind of a problem, you can compensate for it by increasing the mobile phase strength or something like that. And I'm sure you've gone through those kinds of things in your achiral validation. Stability, generally just the solubility of the stability of the analyte solution. We can run, for example, just an overnight run just to show, make repeated injections over the course of time to show that the analyte is stable in the solution, or just a stability study to show that the analyte is stable in the solution. If it's not stable, then the usual workaround is either change the sample solvent or do what we call prep and shoot, just make up the sample and inject it. Okay, so this is probably nothing really new. The only issue is we're dealing with a ratio of a major component to a minor component. But still, I would treat the minor component analysis as an impurity. And so the things that you and your organization do for analyzing impurities would be fairly similar to what you would do with analyzing a chiral component. Improve method robustness. I have these kind of listed in this order. This is not, I think as part of method development, you want to do the method robustness. You don't want that to be a test that you ran later and are surprised by the results. In fact, I think you want to already know what's going to happen from validation. You should have already done some of the experiments around validation to know how good your method's going to work before you hand it off to the group that might validate the method. So the validation and should really just be a formalization of what you already know. Method robustness, I think, is something that should be incorporated in your method development. So we talked about this earlier, where we saw some change in retention of this endocrine disruptor as we changed the mobile phase solvent. And I said, well, we can make little plots, and this gives us a kind of a visual way to see the change. And I hadn't really noticed that before I did this, but I didn't really think quantitatively about what this curve might actually look like. So I think it's worth plotting the data, and it's worth having not just one or two data points, but it's worth having a data set to make sure that you see what the nuanced behavior is. In this case, it's trivial. It's fairly easy to visualize, and maybe not worth a big study, but still have the ideas. But if we go to something that's a little more complicated, then we probably want to do a little more sophisticated study. This is separation of this diastereomer. So I have four peaks. And screening on, I got several separations, but I like this one because the peaks were fairly sharp. So I thought I would try to do the separation on this column with this mobile phase. Unfortunately, in the screen 50-50 methanol ethanol, I got one of the peaks, one of the enantiomers resolved from the other three. So I did some other experiments. I varied mobile phase and I varied temperature, and it looks like kind of the data's like all over the map, so to speak. So I think we need to look at this a little more systematically. And actually, these experiments were done in a fairly systematic way. I varied the mobile phase composition from 3:1 to 1:3 methanol ethanol. And for each of these, I varied the temperature, high temperature, low temperature. So With more complicated data, particularly when we have two parameters and it looks like there is some behavior that's a little more complicated, it's often useful to think of this sort of like a factorial design. And what I do is I'll go into a conference room or lunchroom or something and find a table where I can just lay my data out and lay the chromatograms out in the way that they were run, so to speak. And so I can compare, okay, so this is at 1 to 3 methanol, ethanol at high temperature and low temperature. And as I look at it, oh, okay, so I can kind of improve the separation as I go to higher temperature. But at 1 to 3, I look at this and it looks like, the temperature actually improves, separation improves as we go to lower temperature. Statisticians refer to this as interaction, where you have two component, you have, for example, two parameters, and if you set one of the parameters, the behavior, say like this, we see improving separation at higher temperature, and if we set this parameter at a different level and rerun the experiment, say varying temperature, we see a different behavior. They call that interaction because the actual response, in this case separation, is dependent upon the combination of the independent parameters, mobile phase and temperature. And this can be very confusing. So run it at these two experiments and just vary the temperature and see what that behavior is. Well, I thought maybe I can go to some extremes, either higher temperature or go to straight alcohol. That didn't work out. So I will, but what I did learn is I did learn the separation wasn't going to work and there wasn't any sense continue to beat my head against the wall and so I went to a separation on another column. But this is a factorial design, and sometimes just draw this little box with the different parameters levels, and and we have a center point. I like to do that just because this is often the starting point, and we make the box around that. This is 5 experiments for 2 levels. That's not too bad. And notice the parameters are easily changed, so we can do that in an overnight experiment or just set it up to the day and come back in a little bit and get your results. It doesn't require that you necessarily know what the results are before you do the next experiment. You just have the experiments already run. In fact, this is how you'd fill in a table. We can also just look at the extremes. It's okay. This is our center point, so we'll hold the temperature constant. We'll see what happens when we go to straight ethanol, what happens when we go to straight methanol. Hold it 50-50 methanol, ethanol, and what happens when we go to low temperature and high temperature. 40 degrees is the upper column temperature limit for these columns. 10 degrees is a convenient temperature that most LC temperature control compartments can reach. Statisticians refer to this as main effect. Means everything's held constant. We're just looking at the behavior of one parameter change with everything being held constant. So if you want to, you can, it's statistically defensible because statisticians have a name for it. So you could still at least run these experiments. And this is still a systematic approach. You have some idea. You don't know about the interaction, but you do know what the bulk effects is. And I would certainly at least have the center point and perhaps some other data points along this. I often use central composite design because it just is more space filling, gives us more information. But certainly, at least just the main effects is probably an experiment worth running. So this is an experiment that I ran, separation. This was a screening conditions. Had pretty good separation, 1-to-1 methanol, ethanol. Thought, well, let's see what happens as we increase the methanol-ethanol ratio. Let's see what the effective temperature is. And so this is a high level of methanol, ethanol, high temperature, low temperature, low level of methanol, ethanol, high temperature, low temperature, simple factorial design, but you don't even need to plot the data. You can look at it. High temperature is going to give us better separation than lower temperature. And methanol and ethanol seem to have no effect. The ratio seems to not affect the separation very much. So why don't we just go to straight alcohol, and why don't we go to high temperature? That's pretty obvious from these series of experiments. This was 5 experiments to come to that conclusion. We didn't actually need to run all these star points. or main effect points. I knew that I wanted to use alcohols at the upper column temperature limit. And so I then just ran those experiments, got a similar retention. Interestingly, the ethanol peaks sharper than the methanol peak. So probably if the later eluting peak is our component of interest, we definitely want to use ethanol versus methanol. But there are some advantages to methanol. One is it's less viscous, so we can probably run it we can run it at a higher flow rate. The other is if this is your main component, this is your analyte minor component, this is your main component, you get better dynamic range because this is probably twice the peak height given the same amount of material. So if you make this at a higher concentration, this peak will be big, but the relative height of this peak will be taller than the relative height using ethanol. So there can be an advantage to having a broader, shorter peak for your main component. And we found this by a systematic approach. It's almost trivial, but I think it was unambiguous. Okay, so these are the things we talked about improving the robustness. Fundamental chromatographic equations help us to predict some of the behavior, make use of library screening. We want to have sharper peaks, evaluate the different alcohols, shorter columns give sharper, taller peaks. So generally want to choose conditions that give us sharp peaks, especially for the minor component, and use of experimental design. Whoops, I'm sorry. And use simple conditions. Less things can go wrong. So in effect, that's what I hope you learned here is that achiral, what you know about achiral chromatography applies to chiral chromatography. Much of what I showed you could have been an achiral talk. Talked about validation. It's very similar. Method robustness, importance of troubleshooting, a systematic approach versus a random walk, and the idea of keeping the separations simple. So the last thing is what we can do to help. So we can provide column screening for you generally at no charge. There can be some complications, but in general, there's no charge for that. We'd much rather sell you a column that we know is going to separate your analytes than to sell you, say, a Chiropac IA, which is a really good column, but I have no guarantee that's going to separate your compounds. I'm always glad to talk to people about chiral chromatography. This is my email. This is my email here. My colleagues and I monitor this email box, and we can answer questions if you want to send it to there, or if you want to send it there and also CC me, I'll get it both places. We have a phone number, you can call us, and we have a website, chiraltech.com. Okay, this is my favorite slide because it means I'm through talking, and this has my email address. If you have questions, send me some emails, and I'll be glad to discuss this with you.
Thank you, Bill, and thanks to all of you for attending. We hope you enjoyed our webinar. Please do not hesitate to contact us with any questions, and stay tuned for our lineup of webinars coming in 2020. Have a great day.